Transformer. What is transformer? The definition of transformer is it's a static electric device to transfer power from one circuit to another circuit without changing the input supply frequency, working under the principle of mutual induction. This is the definition of transformer, right? Okay. Generally, the transformer consisting of two windings or two circuits. One is primary circuit and another one is secondary circuit. The primary circuit consisting of primary winding and the secondary circuit consisting of secondary winding and load. So the primary winding, which is why they called so primary winding, a winding to which connects the input supply to apply the supply voltage. For similarly, for secondary winding, a winding which is connected across the load, which is known as secondary winding. Then the two windings are coupled through the iron core. This is the rectangular iron core, right? In this iron core, which is made up of on a laminated sheets. Laminated sheets. Why they laminated? For reducing the eddy current loss. Eddy current loss is one of the magnetic laws. Actually, this is a magnetic circuit. So the magnetic circuits having two losses. One is eddy current loss and another one is hysteresis loss. For the purpose of reducing this kind of magnetic losses, especially for eddy current loss, the cores are laminated here, right? And also the iron core provides a path of magnetic flux, especially low reluctance path of magnetic flux, right? So this is the transformer, right? The winding here, the winding which is made up of on a copper or aluminum, right? For both primary and secondary winding, right? What is NP? The term NP refers to number of turns in a primary winding. Similarly, NS, number of turns in secondary winding. And VP, input supply voltage. VS, output supply voltage or secondary voltage. And IP, current flows through primary winding. IS, current flows through secondary winding. The term Q refer for flux, magnetic flux. Okay, so this is the general arrangement of transformer. Okay, we see one by one. We see the working principle and the construction of transformer. Construction details of transformer. The next slide. So the primary winding connects input supply, secondary winding connects load, the output voltage, right? Then the transformer tank also contain transformer oil. The total transformer core and windings are immersed in the transformer oil. So what's the purpose of transformer oil? We provide here to reduce the temperature rise. The transformer at the time of operating with the load, the temperature gets increases. So at the time they require cooling. So the transformer oil will act as a cooling media, right? So the oil have high dielectric property. The oil have high dielectric property. It's free from acidity also. It's free from acidity also and low viscosity, right? And also the transformer oil can be used to protect short circuit between the transformer windings and the transformer tank. So two purpose of transformer oil. The purpose one is cooling media and another purpose is prevent short circuit between windings and transformer tank. So the transformer oil having high dielectric property, right? So the whole arrangement of a transformer immersed in the transformer oil, and also they placed inside the transformer tank. So this is the cooling tube for for giving air cooling to the transformer windings, right? It's the radiator or cooling tube. And then the winding terminals are connected to the insulated terminal. So the why insulated terminals are provided here to prevent short circuit between the transformer tank and the winding terminals, right? So this is the insulator terminal or bushings, terminal bushing. So the terminal bushings connected connected the winding. Similarly for primary winding and secondary winding, terminals are connected to the bushings, right? This is the insulators. And another thing is conservator tank. So the use of conservator tank is, so some of the excess oil stored in the conservator tank. Why the conservator tanks are used? And the transformer operating under loading, at the time temperature may rises, current increases, temperature rises. So the oil get expanded. Oil get expanded. So at the time the expanded oils are goes to the conservator tank through this tube. Suppose there is no conservator tank here, what happen? The whole arrangement get burst due to the expanded oil. Okay, so for that purpose, we have to provide the conservator tank. Then after normal condition, or otherwise we can say that after no loading, the temperature reduces, the expanded oils are stored in the conservator tank, again come back to the transformer tank, right? Through this tube. The conservator tank connected between transformer tank, connected to the transformer tank, right? Here, one more arrangement is the Buchholz relay. The Buchholz relay connected between conservator tank and the transformer tank. The two purpose of providing this Buchholz relay. So light fault, minimum fault occur at the time the Buchholz relay gives only signal. Suppose severe fault, the current rises heavily. At that time, the Buchholz relay operates and disconnected from the supply, right? So this is the use of Buchholz relay and breather. So breather is a cylindrical tube. It contains silica gel. So the silica gels gives absorbing the property of silica gel is absorbing wet air. So sometimes the air gets inside the transformer tank The time they permit only the dry air. If wet air get inside the breather, the silica gels are absorbs the wet air, only they can permit dry air to the transformer tank. If wet air permits, what will happen? The transformer oil loses its dielectric property. So never wet air permit inside the transformer tank. Okay. Okay, this is breather. And then drain valve. So sometimes the property of dielectric property of oil loses. At that time we are in need of removing the carbonized oil, the heavy carbon making the losing of dielectric property of the oil. So at that time we are in need of remove the carbonized particle of oil. It contains high acidity and more carbon, so they causes reducing the dielectric property of the oil. So that kind of oil have to remove by the drain valve, the transformer tank. The drain valve fixed in the bottom side of the transformer tank, right? So this is the construction details of a transformer. It contains, the parts contains laminated core, discussed, windings, primary winding and secondary winding, insulating material. Insulating materials are provides top side of the transformer tank, and the transformer oil. The transformer oil keep inside the transformer tank. Tap changer. Tap changer generally used for the secondary winding, for getting different operating voltages. For that purpose, they are providing the tap changer. Then oil conservator. So at the time of load, the temperature rises, the oil get expanded, so the excess oils are goes to the conservator tank, right? Then breather. The breather only permits the dry air. If the breather permits wet air, the transformer oil loses its dielectric property. So this is the purpose of providing breather. And finally, cooling tubes. For providing cooling media, here the cooling tubes are there, right? So this is the construction details of a transformer. Okay. The next slide, working principle of a transformer. So the diagram shows the transformer. The primary winding is the secondary winding. And left hand side is primary winding, right hand side secondary winding. The number of turns in primary winding is NP, number of turns in secondary winding NS, right? It's the iron core, especially for laminated iron core. Why the cores are laminated? To reduce the eddy current loss, right? And also the iron core provides a path of magnetic flux, especially for low reluctance path of magnetic flux, right? Why this is primary winding? A winding which is connected across the input supply. This is primary winding. A winding which is connected across the load, right? This is secondary winding. The winding which is made up of a copper coil or aluminum coil, right? Now you see the working principle of transformer. AC supply voltage is given to the primary winding, and after passing AC supply voltage, current flows through the primary winding. This current causes the magnetic flux, a flux set up by the primary winding due to this current. This current is known as exciting current. Why they call so exciting current? The force required to give the flux. The force is current. So this is exciting current. So due to the exciting current, a magnetic flux set up on it, right? And the same flux, the nature of flux is alternating one. Alternating means the flux can be varied from 0 to maximum, again 0, then negative maximum. Should look like a alternating one. Should look like a alternating one, right? So the alternating flux cuts the winding, cuts the primary winding, EMF induced on it. The EMF is known as self-induced EMF. The self-induced EMF always opposing the supply voltage which cause producing light according to Lenz's law. Okay, the self-induced EMF is always opposing the supply voltage, right? At the same time, the magnetic flux inside the in phase with the primary current, right? The supply voltage lags behind the magnetic flux, right? Lags behind by 90 degree, right? Then the flux cuts the primary winding, EMF induced on it. That kind of EMF is known as primary induced EMF. Okay, or otherwise we can say that the self-induced EMF, right? Okay. Again, the same flux linked to the secondary winding also. Here, both primary winding and the secondary windings are coupled, but there is no electrical connection between them. There is no electrical connection between them, only magnetically coupled by the iron core. There is no electrical connection between them. The electrical connection only given to the primary winding, not for secondary winding. Okay, so the flux linking to the secondary winding is a mutual flux. Due to the mutual flux that cuts the secondary winding also, so EMF again induced on it. EMF again induced on it due to the mutual flux. That EMF is known as mutually induced EMF or secondary induced EMF, right? The secondary side. So the EMF which in turn power, input, output power, the current, output current and then output voltage which in turn output power. If the load is connected across the load, the power can be delivered to the load, right? So the output voltage may be increase or decrease. So the output voltage can be depends upon the number of turns provided in the winding. The secondary winding, suppose the secondary winding having more turns, the output become more. The number of turns in secondary winding is less, the output become less. Okay, right. So suppose the number of turns in primary winding is more than that of secondary winding, so the output become more. So the transformer is known as step-up transformer. Suppose the number of turns in secondary winding is less compared than the top primary winding, kind of transformer is known as step-down transformer. So the two transformers are the step-up transformer and step-down transformer, right? So the step-up transformer and the step-down transformers are classified based on the output voltage, based on the output voltage, right? So this is the working principle of transformer. Wait. The diagram shows the windings. So the another classification of transformers are core type transformer and cell type transformer. So these are all core type transformer. These are all the cell type transformer. Okay. So what is core type transformer? This is the coil or winding surrounded by the core. It's known as core type transformer. Here, cell type transformer. The core is surrounded by the coil or winding. This is cell type transformer, right? So core type transformer, cell type transformer. What's the difference between these two? First difference, the coil or winding is surrounded by the core in the core type transformer. The cell type transformer, core is surrounded by the coil or winding. This is the first difference. And the second one, here only one path of magnetic flux. Here only one path of magnetic flux. Here one more path is there. Two path of magnetic flux. The first path, this is the second path. The center portion, two magnetic fluxes are meets in the center portion. They give more flux. So practically, we are using the cell type transformer, right? So this is for three-phase transformer. This is for single-phase transformer. The another classification of transformer is single-phase transformer, three-phase transformer, based on the input supply. Single-phase transformer and three-phase transformer, right? Based upon the core construction, core type transformer, cell type transformer, right? Right. This is the core arrangement. For cell type transformer core is for core type transformer. Is for core type transformer. Right. So in this cell type transformer, E type laminations and I type laminations core. The cell type transformer, E and I laminated steels are used. So the bunch of E and I laminations make a iron core. So the iron core having bunch of E and I type of laminated sheets. Similarly, core type transformer, two L type laminations are used. Laminated steels are used. This bunch of laminations make a iron core. Okay, this is the core arrangement. The core, which is made up of a silicon steel, especially for laminated silicon steel, and also the sheets are made up of a CRGO, cold rolled grain oriented silicon steels. So for making or reducing the eddy current loss, the cores are laminated, right? So far we discussed the construction details and the working principle of transformer. Now we go for EMF equation of transformer. So before find out the EMF value of for both primary and secondary winding, we have to consider some terms. So what are all the terms? The first thing is N1, number of turns in primary. N2, number of turns in secondary winding. Phi m. Phi refers to magnetic flux. In phi m, maximum flux in the core. The unit of flux is Weber. For calculating the maximum value of Weber flux, it's called Bm into A. What is Bm? B for flux density and Bm for maximum value of flux density. A stands for cross-sectional area of the core, iron core. Right? The term F refers to frequency of input supply in hertz or cycles per second. Right? So these are all the terms we consider. Right. Now, before deriving the EMF equation of transformer, we have to consider the Faraday's laws of electromagnetic induction. In the second law, EMF induced in the primary winding or secondary winding. EMF induced in the winding is proportional to change of flux, rate of change of flux, right? When the flux changes, EMF also changes. If the flux does not changes, no change in EMF, right? You see the sinusoidal waveform. The sinusoidal waveform is alternating waveform. the flux waveform, alternating nature, so changes from 0 to positive maximum, again 0, then negative maximum, then 0. So varying alternatively, right? So this is the alternating flux. So the flux changes. The flux changes automatically. EMF also changes, right? So now we are in calculate. We are in need of calculate the rate of change of flux. So first change of flux. How we can calculate change of flux? The change of flux from 0 to maximum. Change of flux from 0 to maximum is equal to phi m. So the time taken to complete the maximum value of flux is T by 4f. How the time T by 4f came? Actually, this is the complete cycle. The frequency, cycles per second. T is equal to 1 by f. Then this is the half cycle. T is equal to 1 by 2f, half of the frequency. So this is the maximum value of flux. The corresponding maximum value of flux, the time corresponding the maximum value of flux is 1 by 4f. This is 1 by 2f, this is 1 by f, this is 1 by 4f. So the time taken to reach the maximum value of flux is 1 by 4f. Now by Faraday's laws of electromagnetic induction, average value of flux is directly proportional to rate of change of flux. Change of flux is phi m. Rate of change, the time taken to reach the maximum value of flux 1 by 4f. So after simplifying, we can get 4f phi m Weber per second or in volt, right? Now, rate of change of flux per tan, it means induced EMF in volts. So the average EMF per tan. So far we can calculate. We have calculated only single tan is equal 4f phi m in volts. So for any AC circuits, we have to calculate the RMS value. So how the RMS value of EMF calculate? By using this formula, form factor is RMS value by average value, which gives 1.11. So by using this formula, RMS value is equal to 1.11 into average value, right? If flux phi m varies sinusoidally, then RMS value of induced EMF is obtained by multiplying the average value with form factor. Okay, so multiplying the average value with form factor for calculating RMS value, because the flux varies sinusoidally, right? So average value is 4f phi m into 1.11. So the RMS value of EMF per tan is equal to 4.44 f phi m volt. This is per tan, the RMS value of EMF per tan. Suppose RMS value of induced EMF in primary winding, what we can do? Induced EMF per tan into number of primary turns. This number of primary turns N1. So we have to include N1. So finally 4.44 f phi m N1 volts. Similarly for secondary winding, RMS value of induced EMF secondary winding 4.44 f phi m N2 volts. So this is the EMF equation of primary winding. So RMS value of EMF induced in primary winding is equal to 4.44 f phi m N1 volts. RMS value of EMF induced in secondary winding 4.44 f phi m N2 in volts, right? Okay, already we discussed what is step up transformer, what is step down transformer. Here step down transformer is there. This step down transformer number of turns in secondary winding is less compared than the top primary winding. What about the voltage? Voltage also reduces. So the number of turns N1 or NP is greater than that of number of turns in secondary winding. So what about the voltage? The output voltage reduces. This is for step down transformer. So where it can be used, the places they require low voltage, like charger, cell phone charger. Nowadays we are using cell phone charger. The charger they require low voltage from the single phase 230 volt AC. Suppose we need 5 volt, the 230 volt, the input is here 230 volt, the output is 5 volt, right? So this is step down transformer. The waveform for both primary and secondary winding, there is no change in frequency. Similarly for step up transformer. Here secondary winding having more flux, more turns. Suppose the input is 240 volt, we require 1000 volts. So depending upon the output required voltage, you have to increase the turns. So the voltages are stepped up from the primary, right? This is step up transformer, where it can be used the transmission line for reducing the transmission line losses. Why reducing the transmission line losses? The transmission lines they travel very long time. The time resistance increases, distance increases, resistance also increases. So power loss can be occur in the transmission line. So for reducing the power loss, the voltages are step up in the substation area. So here step up transformers are used. So the voltage level increases and step up voltages are applied into the transmission line. High voltages are applied into the transmission lines. So step up transformer also used in the high voltage transmission lines, right? So this is the waveform of for both secondary and primary voltages. The two phases are same, no changes in frequency. Okay, so this is the definition of step down transformer and step down transformer. Okay, thank you.